All right, and you'll see why I've included the title "Better Safe Than Sorry" with a question mark. First, what I'd like to do is acknowledge that where I live and work in Ottawa, Canada, is situated on the unceded and unsurrendered territory of the Anishinaabe-Algonquin Nation, whose presence there reaches back thousands of years. I also acknowledge that saying this is but a small first step towards reconciliation between Indigenous peoples and newcomers to the continent, with the end point being liberation for all of us. I also really want to give a shout out to Ronnie Minity of NIST, whose actions several years ago in response to a US National Academies Institute initiative really started this whole thing off. So without him reaching out and getting involved with that US National Academies activity, this presentation wouldn't be happening. So really thanks to him. So, outline, we're going to look at the current situation of radioactive sources in ionizing radiation metrology, talk about the disruption to the status quo, look at alternatives, what does a source-free metrology look like, and as I said, some intermediate thoughts in that we're not at the final decision, but I think we're close to some final conclusions. And that intermediate there indicates that input is still welcome from people, and I'm hoping questions and ideas from the discussion at the end of this will contribute to the whole conclusions. So let's start at the beginning. We're all about realizing units. So what are the units we're talking about? And these are the main ones that we deal with in the various sections of CCRI. So we have 𝐊𝐴, we have absorbed dose, both with the units of the gray. We have dose equivalent and its related quantities, the 𝐷𝐸𝐻, which of course is directly related to the gray. We have absolute activity, the becquerel, and its related quantities like specific activity, and then fluence rate and fluence, often used in neutron metrology, but fluence can be used in various areas. So those are the things we're realizing, and it's important, I think, for most of them to realize they're macroscopic. We're not like some of the units realizing a microscopic quantity. It isn't like an atomic clock where we're looking at a single strontium ion or something like that. These are macroscopic quantities where it measures the interaction of ionizing radiation with matter, or it's a characterization of a radiation source or field. And what that means is dissemination requires two things. We require a measurement standard to actually measure the unit, but we also need a radiation field. And I think that's important to start off with, that we have these two things that we need to realize our units. And so the obvious question with the title that we've got is, where are the sources? And so if we look in radiation therapy, this is the equation to realize absorbed dose in the clinic, and you immediately see an isotope there in the absorbed dose calibration coefficient obtained in cobalt-60. In radiation protection, measuring units like HP3 for eye dosimetry, we need beta sources, and here's the NRC primary standard for realizing absorbed dose in that situation. In radiation processing, in sterilization, cobalt-60, as this source rack picture shows, is one of the major applications and major uses for delivering doses of 25 kilogray for single-use medical goods. Of course, in radioactivity and radionuclide metrology, we have the whole list of isotopes, and I apologize a little bit to the radionuclide community online. I'm not going to be talking a lot about that because that's not where there's a huge risk, but it is the widest use of sources in metrology, of course. And then in neutron metrology, survey meters are often calibrated using radioactive sources. So sources span all three of the sections of CCRI. And how are they used? So a couple of examples here, and as I said, I'm going to be leaning a little bit towards section one, and also section 3. So apologies on that, but I think that will apply to everybody. NMIs play the long game. We're needing reproducibility over years. Our clients come back perhaps 2 years, 3 years after their last calibration. They're expecting exactly the same thing. We carry out international comparisons on a period of 10 to 15 years, perhaps even longer. We need to maintain our standards over those years and decades. And so how do we measure performance of our measurement standards to ensure we've got that reproducibility? So here's a simple device. It's a strontium-90 check source. It's a self-shielded geometry. It's about the size of a pineapple. And you put your chamber inside that. It's low activity and it's hardly state of the art. It's things that have been around for many decades. But if they're used correctly, you get this kind of performance. So this is data from our lab. And over 6 years, you see just using this, you can monitor the performance of an ionization chamber to around better than 0.1%. So sources are very good for providing that reference source of radiation to monitor the performance of our detectors. Another example, this was provided to me by Ralph Peter Kapsch from PTB, and this is the performance of their water calorimeter in their cobalt-60 beam. So water calorimetry is their primary standard, as it is a number of NMIs for absorbed dose to water. And what this shows with 3 different detectors, they're able to monitor the performance again at an uncertainty of around 0.1%, which is really, really useful. And sources are really, really good. So it's not under question of how good radiation sources are for providing the stability that we need for our measurements. So how many sources are we talking about? And it's not a huge number for dosimetry and neutron measurements. In dosimetry, cobalt-60, of course, cesium-137 we'll look at in a little bit of detail. We have krypton-85, strontium-90, iridium-192, iodine-125, promethium-147, palladium-103, americium-241. Those are probably the most that we're using in metrology. Other sources are perhaps being used outside in applications, but those are the ones we're using. If we talk about energies, then we're in the energy range from about 20 keV up to 1.3 MeV of cobalt-60. Again, there may be sources higher, but that's the key area. And activities are typically up to 400 terabecquerels, so the sort of 10,000 Curie sources. And of course, in applications, in sterilization, we're up to sort of 1 megacurie sources to deliver those high doses. But in the labs, 400 terabecquerels is about as high as we get. Of course, in radionuclide metrology, it's most of them or as many as they need and increasing as new applications come online. So in radionuclide metrology, you're seeing this rapid increase in alpha emitters for therapy, and that's generating a lot of interest and use within calibration laboratories, but the activities are generally low, and so this isn't really a major feature of this presentation. It's where we've got high activity sources where we're having to consider some disruption. And then in neutron measurements, it's primarily the americium beryllium source and similar devices, or californium, and the energy region there is sort of EV up to about 2 MeV. And activities there are in sort of neutrons per second. So those are the sort of sources we're talking about and what they're used. And these are used on a regular basis in a calibration lab. So let's give an example of a source, and you'll see why we're coming to cesium-137. It's very attractive as a reference field for radiation measurement. It has a single photon energy and a long half-life. So sort of 30 years, and it decays by beta and gives you a single gamma of about 662 kilo electron volts. And that's really nice because it sits in the middle of our energy range of interest. if we sort of think about X-rays from about 10 keV up to sort of 300, cobalt-60 is our upper end around 1.25, and cesium sits in the middle. And it's got this combination of a good energy, long half-life, and a single photon energy. It's not a complex spectrum, so that makes it a very, very nice reference field. And it's available also, key component, available at a suitable activity level. And here's an irradiator to provide that radiation field, and this is from NIST. And it's then used as a way of demonstrating international equivalence. This is the BIPM.RI1K5. This is radiation protection, and this shows from the KCDB the use of cesium to demonstrate ability to disseminate radiation protection calibrations. I won't list the acronyms, some of you will know them without having to have them explained, but it basically covers Europe, North America, Central America, and Asia. So cesium is embedded in the international metrology system for demonstrating equivalence for these services in radiation protection. It provides global acceptance and relevance. And this is where we're coming to the disruption. It's widely used in blood irradiators, which are found commonly in hospitals and blood transfusion centers, and which are being eliminated and replaced. And this is where we're coming to the disruption. So for calibration laboratories, cesium is key and continues to have relevance. In one of the widely used applications of cesium, it's beginning to be eliminated. And why would it be eliminated? Well, let's look at the security risks of cesium-137. It's a uranium fission byproduct, so it's obtained from reprocessing of waste nuclear fuel. So if we look at the fission fragments, cesium-137 sits in that upper peak, and the other common one of strontium-90 sits in that lower. So it's a major product, but it's been coming from reprocessing of waste nuclear fuel. That's not necessarily security risk, but it just gives you an idea of where it comes from. It's in the form of cesium chloride, which is a powder. And this, for sources, is encapsulated, and then in that situation, it's stable and secure, and calibration laboratories have operated these sources for one or even more half-lives without any trouble. But as we know from real life, if that encapsulation is damaged, then dispersible is easier. And the obvious, perhaps well-known incident is from Brazil from 1987, and that was a accidental dispersal in that it resulted from a mistaken opening of a scrapped source. And this is a picture from the cleanup. And so just to give you an idea of the issues that lead from accidental dispersal. And you can immediately realize that if accidental dispersal is bad enough, a malicious release would have very large societal impacts. And with a powder that's easily spread around, that could cause significant panic, or certainly cleanup would be a major problem. Even if the activity as it spreads out becomes relatively low as a health risk, the fear and the cleanup are major impacts. And so this kind of concern and the realization that there are these sources in blood irradiators in hospitals, not necessarily secure institutes, leads to a governmental response, and particularly from the United States, the NNSA and particularly the ORS has initiated a program to eliminate high activity sources from the environment, as it were. And the environment meaning uses outside of critical places. And it's identified 4 key sources and locations. So cesium-137 in self-shielded irradiators, blood irradiators, etc. Americium-241 being used in oil well logging, iridium-192 in radiography, and cobalt-60 has been identified as one being used in research and cancer treatment. And these sources all have applications in calibration laboratories. Now, let's be clear, the ORS is not targeting calibration laboratories. They're not a major concern because they tend to be well controlled, and it's not just in the USA. But if you're reducing the sources in these wide applications, then there's a risk to metrology laboratories in that the sources may not be available. And so for us as a calibration community, we are potentially collateral damage to a well-meaning activity to reduce risk in places where sources perhaps can be replaced. So, obvious question and following up is, are calibration laboratories a safety risk? And they're not really, because they're usually limited access, often requiring going through a number of security clearances to get into a space. They have highly trained staff and multiple levels of security overseen by regulatory bodies. So in Canada, we have the Canadian Nuclear Safety Commission, and they carry out inspections to ensure that we have the appropriate levels of security, barriers in place, alarms and responses. But at the same time, if you have activities which are effectively messaging that all sources are dangerous, any laboratory is at risk, irrespective of the security levels that they maintain. So this is a disruption to the status quo, and in response to that, and again calling out Ronnie Manetti, his raising us to this activities, a CCRI task group was formed. Just to remind you, the CCRI is the primary forum for ionizing radiation metrology at the international level. It brings in all the users, the calibration laboratories, stakeholders, etc. The task group drew representatives from the NMIs from all three sections to get the perspective from all users in our community, also experts from the IEA, and we brought in a representative from the radioactive source manufacturers community to understand the pipelines for source production and to understand what the long-term future was looking like. And the aim was to provide a metrology-specific perspective on this topic. So it's for, obviously, this community, but it's also a report. The target audience for that report are funding agencies, regulators, clients, and users. This is the current makeup of the task group, and as you see, you probably, if you're in the CCR community, recognize these names, but they're spread from across the world and across the different sections. So that's the introduction, outlined the disruption, and so the question that the rest of this presentation is going to look at is, are there alternatives to radioactive sources? And we've got to recognize that if we're talking about alternatives, we have to see that we have a well-integrated system where radioactive sources are used, and change is not straightforward. And what we need to do is look at a few questions when we talk about alternatives. And one is definitions of how to accept an alternative. And this is where semantics is important, and you may find different people having a different interpretation of an alternative. For us as metrologists, very focused on precision, we're probably thinking like for like, that we want an alternative that is exactly as good as a radioactive source if we're going to give that up. But perhaps a funding agency or an end user will only view fit for purpose is good enough. So we have to be clear on what we're talking about when we use the word alternative. We also have to talk about collateral. Are there additional costs we're willing to accept by moving to an alternative? Is it, it may have the same performance, but are there different costs associated with this other system that we might be considering? And then inertia of how do we implement a change? Can we move slowly from one thing to another, or will it have to be very disruptive. And how are we going to deal with that, both within the community and communicating to our end users, our clients, our collaborators, etc. So these are all kind of system things before we even begin to talk about the technology or what's available. And understanding the context of those is essential. So just going back to cesium-137, cesium has become embedded in international standardization. We saw that in the graph of the K5 comparison run through the BIPM. But it's also an agreed beam in which detectors are compared. And so it has becomes a beam that's required for performance specification. And significant knowledge and procedures are built up around the assumption that cesium-137 is available. So if we go to ISO 4037, that standard absolutely assumes that cesium-137 is available as a reference beam, and calibrations are assumed to be available in cesium, performance is tested in cesium, etc. So you sort of see how the source and its universality across the world leads to a huge infrastructure, specifications and procedures that are all built around that source, that energy, activity, etc. So that's an example. In terms of the technical considerations beyond those system things, we have to consider beam intensity. So we have detectors appropriate, say, for radiation therapy, will not have the sensitivity required for radiation protection. So when we're looking at alternatives, we have to ask the question of what is the beam intensity, what is available, and is that appropriate for calibration? And then how do we go from that to an end application? Geometry is also important. Radiation therapy uses a directed beam. Radiation protection assumes something more uniform or a much wider field. That a source intended for one may not be applicable to another. We have to consider this. And beam delivery. If we think of a radioactive source, it is always on. And the speed of delivery is really only related to how the source moves from its storage compartment to its open space, or how a shutter moves, whereas an electrical device may have some output ramp up time, it may have some feedback, it may have some continuous variability. So sort of keeping those things in mind, the task group basically looked at some alternatives, and these are kilovoltage X-ray sources, electron linear accelerators, and other charged particle accelerators, other electrically generated irradiation platforms. So all of these are saying, okay, if we're not going to have radioactive sources, there's some kind of electrically derived generated source of radiation. We also looked a little wider. So what calculational alternatives are there? Are there what called zero radiation options? And we'll come to that in a few minutes. Can we talk about lower risk radioactive sources? Is it that specific sources like cesium, which is a powder and therefore can be dispersed, is a much higher radioactive resource risk than, say, a solid source which cannot be distributed in the same way? And then something that we call cooperative managed reduction, which we'll talk about at the end. Now, this is not a comprehensive list, and perhaps there are people on the call here who might have suggestions, but we think it's not far off of what all the alternatives could be. So let's start with kilovoltage X-ray sources, and what we've got on the pictures there are the new BIPM medium energy KV system. KV X-ray systems have the highest level of precision reported for electrically generated radiation. So we sort of look at short term, we're getting below 0.01% perhaps on a set of repeats. On a few days to weeks, we might have a standard deviation on repeat Kerma measurements down to below 0.05%. And then over longer timescales, over a decade, slow drifts may be only 0.1%. and BIPM have got perhaps the most comprehensive data that I've seen, suggesting that that sort of drift of 0.1% is actually a tube output, not the standard, and that perhaps limits indicates the limited performance of X-ray systems. So this is the data that David Burns at the BIPM supplied. So this is calibrations using their free air chamber multiple detectors, and as you see, the vast amount of that data sits within plus or minus 0.05%. And that suggests, and 0.05% is probably sufficient for long-term for metrology. We'd like it to be better, and I think if we look at cobalt-60 data, we can certainly get better than that over longer periods because of the predictability of source decay. But 0.05% would be better than fit for purpose, if not potentially like for like. And just to be clear, although the BIPM system is most definitely specialized, it's not out of the realms of reproducibility for other NMIs. It's an achievable system, it's well described, it could be reproduced. But, and there are always buts, as we'll see through all of these examples that we're looking at, the photon energy is low. So typically in calibration laboratories, we're operating up to a tube voltage of 300 kilovolts, which gives at most an average photon energy of around 150 keV. And that is not representative of most applications. As we saw in that example about cesium, 600 keV is sitting perhaps in the middle, even if that's a bit on the low end compared to some high energy accelerators. 150 keV is well down at one end of the photon energy spectrum that we're interested in. We know from extensive measurements that radiation detectors can show large energy dependencies and rotational variations in keV beams that are not seen at higher energies. So you might see, if you're sort of establishing performance, you can't necessarily predict from measurements in keV what will happen in high energies where they're going to be used in the end. So it makes prediction of performance more difficult. And interestingly, at low energies, we've seen from the recent ICRU 90 report, interaction coefficients as we go down in energy below 100 keV are not precisely known, and this impacts theoretical conversions between materials and impacts the simulations that we use to support our measurements. And so there are the issues there where it's not exactly ideal. But what we've seen with performance and with that increase looking at simulations at low energies, that KV beams perhaps could play a more generic reference field role than they currently are. They could be considered not necessarily as a direct replacement for everything, but I think could play a role as a reference field. Question obviously is, how high can KV sources go? And it's interesting that although today we're doing sort of measurements up to about 300 keV, in the 1930s we saw a rapid increase in X-ray energy. And so a paper from the 1950s reviewing therapies using up to 1000 keV, and on the picture there, courtesy of the AAPM History Committee, 1936, a 1 megavolt X-ray system installed in St Bartholomew's Hospital. Now you see the size of the device, it's perhaps not something we'd want to use, but the wheel has been invented. It is possible to make a 1 megavolt X-ray system, which would, with the right filtration, give you an energy much closer to cesium. And what we're seeing today is a push beyond that 300 kV limit. Vendors will produce tubes for industrial radiography up to about 600 kV at the moment, and several NMIs are carrying out investigations up to about the 450 kV level. Now, of course, we've got to keep in mind 450 kV is still only sort of 220 to 50 keV photon energy. We're still at the low end of the spectrum, but it's beginning to push upwards. But currently we have limited data above 400 kV. There are limited devices above 450 kV. In my searches, there's one manufacturer I could find, but not a lot of options at the moment. And again, when we're thinking of extending technology and having an example from, say, the BIPM there in that data of what you could do for 250 kV, it's not necessarily the same as possible if you push up to 450, up to 800 kV. The ability to maintain stable power supplies and tubes has not been demonstrated. So it's not straightforward to say, well, it's possible at 250, so it must be possible at higher energies, so we have a solution. I think that's still to be demonstrated. So electron linear accelerators, that's an obvious solution perhaps. They're widely used in cancer centers. Thousands of devices are out there. They're in operation in many NMIs. They're attractive because they provide both photon and electron beams. So now we've got two sources for the price of one, as it were. We've got multiple energies and multiple dose rates. And so we can vary a whole range of things from energy, dose rate, field size in a controlled way, and their known technology. But, and here's the but, let's talk about energy stability. This is data from our accelerator, and here you see measurements of beam quality for our 3 photon energies over about 8 years, actually almost 10 years. And you see that things are generally okay at the plus or minus sort of 0.5% level. But what we see as components fail is a significant fall off in the energy. And this has implications for quality assurance and how much work we have to do. So this is a measure of the collateral I talked about, that a source is a source, and you know exactly what it is, and you know what the decay means for its activity, whereas for an electrically generated device, you've got to worry about the stability of the energy and the stability of the output. So this is looking over the last sort of 5 years of the stability of our absolute output of the accelerator. And, you know, it's not bad, but it's certainly not 0.1%, and it's definitely not 0.5%, which is what we saw with KV X-rays, and is routinely possible even with a simple radioactive source. So it can give you some level of repeatability, but it is not what that we want. And there's a lot of equipment in an electron linear accelerator that can fail. And this is the report from the APM Task Group 142 on quality assurance. I don't want to discuss any of this, to say that this was the annual QA, and this is what's required just to get 1 to 2% constancy. So if we're talking NMI level at the, can we get to 0.1, 0.5% maybe, gives you an idea of how much QA you need to put into place and maintenance to ensure that you've got this reference field from a linear accelerator. For a cobalt-60 irradiator in comparison, our QA is we check the field size, we check the SSD, and we verify that the source comes out to the right place, and that's it. The difference is very stark. So, electron linear accelerators, a bit of a summary there. There are different systems, but there are obvious no ultra-stable device currently available. The energy is not well known, and it's difficult to determine. Didn't say this for KV X-rays, but the intensity of the beams means that it is possible to measure the Bremsstrahlung spectrum directly from an X-ray unit. It is not possible to do that from the current linear accelerators that are available. So we've already lost some information that we get from a radioactive source. Absolute beam current is not a major focus for vendors. They're making devices for radiation therapy. And the absolute output is determined on a daily basis, and it only needs to be known at a certain level that is not what we need. So it's possible that a stable beam could be produced, but knowing what it is not so clear at this point. And custom designs may be necessary to give us a device that meets our requirements. And I just found this recently. This is interesting because it's looking about a replacement for cesium-137, and NMIJ are looking at a custom irradiator, LINAC, to do this. And maybe that's the route we've got to go as a community. But it's not that we can simply go to a vendor and find a device right now. Proton accelerators, I think we can eliminate those straight away from the discussion in what is currently available because of the size and cost. They are an order of magnitude more than a linear accelerator, so they cannot be considered a realistic alternative. In addition, it's worth highlighting that the knowledge base for proton interactions and operation is much smaller than for other beam modalities. NMIs have been using KV X-rays for more than half a century. We've been using linear accelerators for maybe a similar amount of time. A steep learning curve if we were to shift to proton accelerators as a reference beam. So again, there's a collateral that we have to take into account, making that kind of disruptive change. And in terms of performance, this is some data that we acquired with our calorimetry at a proton beam at Triumph in Canada. And you see that with a modulated spread out beam over a short period, we're getting pretty good performance. So that's nice. But on the left-hand side, the measurements with a pristine Bragg peak, and the first 2 points were one day, the second were another day, we're seeing significant variations. So output and energy again become an issue for proton devices. This is not comprehensive data or saying all of them are variable at this level, but it just raises that we don't have at the moment the same level of confidence in these kind of devices. So then, if current devices don't work, are there new accelerator technologies available? And we have to admit that the machines that we're using in our NMIs, our linear accelerators, are actually old tech. A lot of the equipment is really 1960s, 1970s. So is there anything new? And there are new devices being proposed, dielectric wall accelerators, laser-based systems, and maybe these could provide the necessary radiation fields. This is a publication from 2021, this concept of accelerator on a chip, where you're using a laser to create an electron beam. And here we have an amazing accelerating gradient. They're reporting of 700 MeV per meter. So very, very compact devices. At the moment, not very high intensity, but perhaps they can begin to address this gap between what current technology can provide and what we need. Size is a bonus, but maybe not necessary. We're not clear of how tight the energy spectrum can be. Early systems are quite broad in terms of their spectrum, which is not ideal. They could be game-changing, but at the moment it's still an active research field in just providing the devices. We haven't even gone into any investigations of stability, performance as a reference field, but it's worth keeping these in mind. A lot of that discussion has been all about really X-rays and charged particles, and I need to talk about alternatives for neutrons as well in terms of accelerators. Majority of sources are, many people are using are alpha beryllium producing a neutron, so americium beryllium is the most common. This produces, through a nuclear reaction, complex spectra with multiple neutron energies and photon energies as well. Sources do meet two requirements of a reference field. They're consistent and predictable, but they're not monoenergetic, which would be nice, but they're well used, they're easily accessible, and they have become embedded again in the system for calibration. The other source that's commonly used is californium-252, which is a direct neutron emitter, has a simpler spectrum, and higher fluton sources are possible. And there's a big but here, always a but as you'll see in this presentation. It's doubly problematic. It's a very short half-life, so 2.6 years. For those of us in section 1 who moan about the half-life of cobalt-60, it is even worse for our colleagues in the neutron community, where their ideal source has only 2.6 year half-life. And then we worry about the cost of cobalt-60. Well, californium-252 is $25 million per gram, as I've seen reported. So we talk about the gold price. Investing in Californium would seem to be a place to make a lot of money, or finding a way of producing it anyway. So it's a very expensive source and very short half-life. So an electrical generated alternative would seem to be attractive. And there are devices. Predominantly these are DD-DT devices, and this is one of the units from Thermo Fisher that a number of laboratories use. So a DD produces a sort of 2 MeV neutron. So that's close to these americium, beryllium and californium sources. And then DT produces something around 14 MeV, what we call high energy, although it isn't as high as we would like for all our applications. How do they perform? Always important, and this is information from my colleague Jean-Paul Archambault on characterizing our DT device, and this is changing the beam current and looking at the count rate, and as you see that it is a non-linear response. The repeatability is also at the few percent level. If we sort of accept a non-linearity, even there the reproducibility is not at a level we want. It's similar perhaps to a linear accelerator from day to day, but that's still not meeting what we need. Suggests that this technology, which is not designed really for metrology, it's designed for inspections and activation and other things, is not really meeting our needs. Are there other alternatives? We know that there are other ways of producing the voltage, and some could be made more stable. If you've got a more stable electrical supply of high voltage, can you produce a more stable output? And this is the system at the PTB that I was lucky to visit last year, and they use a Cockcroft-Walton ladder to produce a high voltage, very stable, to deliver a high energy proton beam or deuteron beam onto a target. And the advantage of this kind of device is you've got a whole list of energies there that you can produce, so it's tunable. But at the same time, as with other electrical devices, the stability, and this is over half an hour, we see variations that require careful monitoring and control that don't look like a radioactive source. So these are very useful for research and they're complementary, but they don't appear to be replacements for radioactive sources. And they're also complex, requiring maintenance, QA, etc. One of the things we have to consider, and when we're talking about devices, we're sort of thinking in this like for like or fit for purpose model, is that we're putting a device into our current laboratories, and we run a distributed model. And so one of the questions we could ask is, do we need to change that model of operation? If the devices that are available don't work, as a community, can we come up with a system that does work? That's a very large disruptive change to how we do things, but perhaps is worth thinking about. And Coincidentally, CCRI 3 has a workshop this summer which is looking at how it can offer very high energy neutron sources for some of the activities they need. And I think Section 1 will need to look at some kind of centralized facility to carry out proton or heavy ion therapy comparisons, because we can't install these in all our facilities. And there'll be a workshop in September on that. As I say, this concept of centralized facilities requires a radical change in how we do metrology, and we still need something local to realize to our end users. A single facility distributing to the world is a very, very different beast that I don't think we can really consider right now. Okay, so those are the current options for electrically generated radiation, but we can do other things perhaps, and of course calculations are a key part of all our metrology. We've grown rapidly in the use of simulations in ionizing radiation metrology. So if we sort of think back 25 years, Monte Carlo simulations were just being used to calculate wall perturbation factors or very small aspects of a detector. We spent a lot of time developing a very elegant experiment, minimizing all the corrections, and then we'd use our simulations just to find those correction factors. If we move to sort of now, Monte Carlo can simulate an entire radiation processing facility. This simulation is from Chris Howard at Nordion, and this is simulating products going through an entire facility being irradiated by a cobalt-60 source rack. So we've come a long way in what we can do. We also, in terms of scale, we can go the other way. We've got simulations working down at the very micron scale now. So simulations are a lot more possible, and we have to understand we've consistently underestimated the progress in computing power. The worldwide shock at GPT-4, I think, shows how quickly things can move and what can happen. And so if we're looking forward, this makes it very difficult to predict what computing can do. But it wouldn't be unreasonable to say that, from an accelerator or an X-ray tube, just knowing some parameters of the power supply, we could simulate the output of the device. Absolutely. So, going crazy, just measuring the power into the power supply, it should be possible to give you the X-ray output at the end. So in this situation, you're measuring radiation output from non-radiation quantities, and in that context, you're traceable to the amp or the volt, not to the gray. It is a radical thought in that respect, but you can't imagine typing into the next generation of these large language models of just knowing the mass of an americium beryllium source, the output in terms of neutrons per second. That may be a little on the crazy end, but I don't think it's that far given what we've seen in the progress on calculations. Linking in with calculations is what we could sort of call a zero radiation option. Can we replace some of our radiation source measurements with something else? So if we look at our 𝐊𝐿𝐴 standards, the equation there requires knowledge of the absolute mass of the air in the chamber. And so we go to a lot of trouble to mechanically measure those detectors. And then by knowing that and measuring an electrical signal, we realize a radiation quantity. Can we take that further? Can all chambers, can we realize that absolute mass of air, and then we can perhaps replace a cobalt-60 calibration? All we need is a micro CT and finite element modeling. So this was first proposed back in 2008. in terms of using micro CT to measure that sensitive volume of an ion chamber. And that was followed up in 2012 with using finite element modeling to actually look at the sensitive volume, not just the mechanical volume of any ion chamber. And both CT and FEM have got a lot better over the last decade. So if we can measure the sensitive volume of a detector, and we have our current equation for realizing 𝐊𝐿𝐴, potentially we do not need that cobalt-60 calibration. We can go straight from this to the end user calibration coefficient. But, again, always a but. There was a presentation on this from 2012. We have to realize that an ion chamber is more than an air volume. And one of the things that an end user gets from a calibration laboratory is confidence. We're not really selling a calibration certificate as a calibration laboratory. What we're selling is confidence that the detector that the user has will work, and if you use this calibration certificate, you will get the right answer. We're predominantly providing a confidence in operation. So if we're not providing that confidence, what are we actually doing as a calibration laboratory? Only by making a radiation measurement can you determine that things are working properly, the detector's got the right connections, it's not failing in some way. We've got a history on this device over years that it's not changing, that a mechanical or a CT measurement would not pick up. And ultimately, we are telling the end user that the device will work in its intended environment. And if we're not doing measurements, are we really doing metrology? I think these techniques of CT and FEM have a role, and we see that in publications and in reports to CCRI meetings, but I think it's complementary rather than replacement. I said we talk about lower risk radioactive sources. There aren't a lot of options, but certainly if cesium chloride as a powder is a risk, can you vitrify the source so it's much harder to blow up and distribute? In radioactive nuclide metrology, we're seeing looking at using holmium-166 metastable as a replacement for radium-226. They're possible. The challenge really is partnering with a source manufacturer with the expertise and enthusiasm to develop them for a very small market. These lower risk sources are really only going into, I think, calibration laboratories. There's not a big application, so it's finding the expertise and the willingness to move forward on that. It may be there, but we do need to go out and find that. There's also an idea of, can we lower the activity? Can we, going back to that early picture, can we do a measurement in a self-shielded strontium-90 source, which is very easy and very low risk? Can we use that to issue a calibration? But we have to keep remembering that it's our end user sensitivity that we have to focus on, and there's a disjoint then between measurements with a low activity source at the calibration lab compared to what's being done in the end user, and we have to do a lot to bridge that gap. So again, collateral comes in of what costs are being added to by making these changes. Just want to highlight this sort of depressing scenario. So this is a non-alternative. This is the one where we accept that we're not getting any new sources. We keep the ones we've got, and we try and make the best of a bad situation. This is, you can imagine it's a possibility as we see pressures on from regulators and from costing. But if we sort of spin that round a little bit, is there a concept of using a source for longer than we have done? We've typically, with cobalt-60, replaced it on 1 half-life, maybe 1.5 is there measurement science we can do to extend our sensitivities and still have confidence in our measurements? We're seeing a lot of work in a lot of our colleagues in NMIs with quantum-based sensors are not really coming into radiation metrology. So this concept of going to lower activity perhaps is a way to bring in some of those sensors, which could have applications. But again, this does not consider end user requirement who are still having a high activity or high beam output application. But thinking out these things sort of gets us looking at adjacent technologies which could have an impact in ionizing radiation. So that brings me to the end of the presentation. And so to summarize from our current perspectives on the task group, kilovoltage X-ray sources are a possible alternative as a reference radiation field. There are question marks about energy, but we have demonstrated stability at a level that we would be comfortable with. At the moment, electron linear accelerators and proton accelerators are poor in terms of their operability as a replacement. Other systems are unknown at this stage. I think there's some very exciting science going on and we should monitor it, but as a metrology, a radiation platform, they're not really demonstrated at this point. Calculations will, I think, continue to play an increasing role and could be used to reduce the number of radiation beams we actually need or change the way that we do our calibrations, but they can't completely replace sources. Again, same as zero radiation options, we have to do measurements. If we're going to be a metrology lab that is providing a service to end users, we have to do measurements in radiation beams. Again, looking at lower risk radioactive sources is worthwhile, but it's the application as an alternative is likely to be limited. And so ongoing access to sources we need is a big yes at this point. There are no easy switches, and there isn't an obvious candidate to just go, hey, let's go down this avenue. Same time, there are opportunities. So to summary, finally, calibration laboratories may not be a focus for risk reduction activities by regulatory bodies, but our capabilities are at risk. We have to be very clear on that. The concept of alternatives is attractive. Having systems you can switch off at the end of the day where you know there's no residual radiation is very attractive from administrators, from regulators, but there are no clear replacements at the moment for radioactive sources for radiation metrology. And we have to keep messaging that although some of these may be replacements for other applications, so blood irradiations, yes, you can do it with KV tubes without a trouble. Small animal irradiators, you can do it with KV. Sterilization, you can do it with very high energy, high power accelerators. That is not the same as ionizing radiation metrology. These sources can play a role, but we do need better performance or enhanced operation. They don't currently meet our needs. And simulations will increasingly be used, but barriers remain. There's fundamental data issues still. Absolute accuracy is still not been demonstrated, and it's not clear how far we can apply them. But this all adds up to two things. There are opportunities for research. So for people in the NMIs, people in universities, people in industry, there are definitely places where there's research to be done. But at the same time, there's opportunities for advocacy. We need to be talking to our funders, our regulators, our public end users of how important radioactive sources are, and in the environment of well-maintained calibration laboratories, they are essential. So thank you very much, and yes, if there are questions, comments, happy to open it up.